Hello, welcome to my physics lab 5. This is my fifth and final lab. This is a choose your own adventure lab, and I chose to model the motion of a slinky. So what is the purpose of this lab? This lab's purpose is to model the downward motion of a slinky dropped from rest. And the topics discussed are the energy principle, spring force, gravitational force, as well as work in Newton's second law. So I modeled the glow script. I modeled the slinky in glow script and in real life, and used tracker for the real life model. So what are the fundamental principles? Newton's second law, which states that the acceleration of an object is dependent on the net force and the mass of the object. We use the initial velocity to calculate the velocity using the velocity update formula. In this case, we used the computational model to model the motion of the slinky system, and F net is equal to F grav plus F drag plus F of the slinky. So what is the system and surroundings? The system is the slinky, whereas the surroundings are the earth and the ground as well. The initial conditions, these were found based on the tracker. So the initial conditions are as follows: the initial position, the initial velocity, and then the mass, and then j hat, which is the vector pointing in the direction of the slinky. So this was the tracker experiment. We used the video that was provided to us, and then I deduced the position versus time using the tracker software. So this is the code. This shows what was used to generate the glow script computational model, the mass is input, as well as the position, the initial position, as well as the initial velocity, and g is input, as well as j hat, and then the drag force is also input based on, the drag force was found based on the real life model using the tracker. And then we input these values into the computational model to create a model that best fits both the initial and the final conditions. So discussion, the position versus time graph models show that the graphical model is a good representation of the object's motion, as well as the computational model provided accurate data about the object's predicted positions. As you can see, the predicted and the observed are very similar. The glow script model and the tracker lined up pretty much all throughout the experiment. So some sources of error. Some sources of error are the blurred motion from the tracker, as when you take the video, the slinky is a little bit blurry, so some error could have been done when selecting the points, as well as the drag force was not accounted for, and then human error, as initial condition calculations may have been a little bit skewed. So what does it mean? The question was, does the bottom of the slinky remain stationary in the model? And then, if so, why does it remain stationary? And what would make it not stay stationary? So I said yes. The bottom of the slinky does remain stationary because the magnitude of the tension force in the slinky is equal to the magnitude of the gravitational force, and the net force is equal to 0. Therefore, the y position at the bottom of the slinky stays stationary. Whereas if the net force was not equal to 0, then the y position would not be stationary. And as a result, you would have the bottom of the slinky move rather than stay stationary as it was in this example. Thank you.